Okay. First of all, I thank the organizer to give me the opportunity to talk on my work. I'll be talking on pattern formation in hydrodynamic simulations, and which are very closely related to some of the uh, plasma experiments done a few years ago. So, in general, we know that turbulence is a very interesting problem from many perspectives, starting from atmospheric turbulence to turbulence in galaxies to fusion devices. But for all sorts of turbulence, there are interaction between different length scales. And so understanding the interaction between different length scales is very important. And that's why this asymmetric term comes in. Sorry. So asymmetric means the interaction between two non-identical length scales. So here I will be talking about mostly two different vortices of different sizes, which will be interacting amongst each other. And then we'll see for which cases it forms a pattern, some sort of self-rearrangement or something, or and for some, how do they form those kinds of patterns, etc. So we know from standard turbulence texts that vortices are eddies of comparable sizes. When I say size, I mean uh, the K defines the 2 pi over L, the size of the vortex. So eddies of comparable sizes can generally comparable may not be exact, but comparable sizes can interact. However, if you have two eddies of completely different sizes, for example, one is very long eddy and another is very short eddy, then typically the short eddy gets advected with the in this big eddy. So they don't directly interact. So that's why I said the disproportionate eddies, that means completely different eddies, different sizes of eddies do not interact like this. So interacting vortices, which are like of the same comparable sizes, they interact and they beat together, and then the beating is essentially a form of merging of the two vortices. So, but here we will be focusing on some cases where we'll see eddies of completely different length scales. How do they merge? And more interestingly, later on, how do they form some patterns? There has been several experiments on this kind of asymmetric vortex merges. And if you want to look up some of the previous, if you were to look up some of the experimental setups, one is this, when you can look at this sort of things, because they generally initialize some sort of a electron cloud in the chamber, and then then run the experiments and make a movie using the CCD camera, and then do all sorts of stuff. But what is interesting here, this is a plasma, and what I was talking about there is neutral fluid, because we know that there is a homology between the ideal magnetized plasma coulombs and a strong axial magnetic field and incompressible invasive 2D turbulence. So the equations look pretty similar up to some boundary conditions. So with this sort of introduction, let me define the system that I'm as of now trying to simulate. So we'll be considering, so first of all, we define two population of vortices. One we call small, another we call large. So we have only two population currently. The small vortex will be called as point vortex, even though for numerical purpose, we do not consider them as exact point. They have some very small width, depending on the, if you have very high resolution, you can make them smaller. And you have another, which is a large vortex, which we call patch vortex. This is typically something like a Rankine vortex, where the vorticity is uniform in the patch. If you want to look, so this is one sort of initial condition where you have very strong 2 point vortices here and 1 patch vortex here. If you want to look up some experiments and comparison with experiments, there has been several works earlier. One example is this one. So this is the experiment and this is the simulation. It's an old work. So here they start with 1 patch vortex, 1 point vortex, and then they evolve it, and you can see that how good they capture the simulation and experiment, etc. However, we have some different notion, but I'll be talking on that. So after defining what is point and patch, let's first we'll have to be clear that where we will put this point vortices. So we have mentioned that the point vortices are placed close to the patch vortex. So this is the patch, but how close is close? We'll be giving some quantitative explanation of how close is close. Before that, as of now, let's keep it vague that this is something like close to the patch vortex. If you put this point vortex near this patch vortex, these point vortices can excite perturbations on the surface of this patch vortex, somewhere here. The circular uniform, this is the Rankine vortex which I mentioned, circular uniform patch vortex. They support surface waves. So in this surface, they support some sort of waves which we call the Kelvin waves. And the mode number of these Kelvin waves, let's call that m-fold Kelvin waves. So these create some sort of a V state, like wavy structures on this boundary. And if you put, suppose n is the number of point vortex, suppose. So if you put n PV or n number of point vortices around it, it will generate a perturbation, or it will generate a surface wave with mode number m. So m equal to nPV. And these nonlinear, so if you, these surface waves that get generated on this surface of this Rankine vortex, these waves, they are basically nonlinear, and also they're dispersive. They are marginally stable waves, and they actually they actually form, this is something like sort of the V state, which I talked about. And these kinds of structures, they drag out from this circular patch vortex. So these are the things that we call filament. So they filament out from the patch like this. And at late times, these filaments wave break. Here you can see the filaments have turned over like this. So if you look in the radial direction, you'll see that they have something like a theta motion in the theta direction, and then the overbreak means they overturn like this. And they nonlinearly interact between themselves with this. But up to this, the earlier analytical methods was good, but when the filaments wave break, the analytical or contour dynamics method failed, because there are a lot of short scales got generated in this system now. Because here you have something like a overturned patch or something. So now you can see that you have several K generated in the system, several length scales generated in the system. And now the other population, that is the patch vortex, which has generated these different scales, they can now interact. What do I mean by interact? I'll be explaining it later. But now let's come back to the question, where should we put these point vortices to excite the waves? So there exists a formula, which is like the radius of the point vortices divided by the radius of the patch vortices is equal to square root of the number of point vortex by NPV minus 1. So from here, or at least less than equal to. So here, this is how you know where to put your point vortices to excite these perturbations. Now, as I mentioned in the last slide, they overturn and they sort of encircle this uh, point vortices. These overturned or wave broken filaments drawn out from the patch vortex now encircle the point vortices. And let's now try to answer why do they interact. Uh, I mentioned the homology between this two-dimensional incompressible inviscid hydrodynamics with the 2D drift Poisson model. So if you go to this reference, you will see the energy density of the surface. They have mentioned the energy density of the surface waves is always negative. When they mention these are in terms of density, and what we call vorticity, they have it in terms of density of the electron. So it's something like the gradient of the density, number density of electrons. So you can see the energy density of the surface waves, that is the filaments, is always negative when they propagate in the direction of rotation. However, the energy density of the point vortices are positive. So the difference in the sign of these energies, that is the filament and the point vortex, makes possible an instability in which the point vortex moves radially inward while a surface wave grows with the total energy conserved. So I'd like to show a small movie for that. You can see here that this is how the surface waves generates. They go, they overturn like this sort of, and these are completely nonlinear structures. And if you wait further, they go inside and they form something like, so this part is something which is a region of zero vorticity, this black part. And as it moves forward, this region of zero vorticity gets trapped here. So now you have a vortex. Sorry, now you have a vortex and a hole pattern. So this is the kind of pattern you observe as you run the simulation. So the filaments encircling the point vortices form vortex hole patterns. This pattern move radially inward and stir up the patch and finally stabilize, forming vortex crystals. So these have been confirmed earlier by Ganesh and Lee in 2002 by PIC simulation. And later we did some fluid simulations. And we compared the results up to 15 largest eddy turnover time. And we checked the conservation of the Casimirs. Here I give the parameters of how to simulate this. This d equal d gives the size of these point vortices, etc. Now, all those things were in the incompressible regime, incompressible 2D hydrodynamics. The homology between the hydrodynamics and the 2D drift Poisson model of electron plasmas break now if we go to compressible regimes. Here, if you have a compressible fluid, the compressibility allows sonic waves. And for our simulation, we have pseudospectral simulation with some sort of de-aliasing treatments. And we cannot go to very highly compressible fluids. So we restrict ourselves to weakly compressible fluid of Mach number like this, 0.3 to 0.8. These are the governing equations. And so in this part of the talk, I'll just extend the same problem to the for the compressible fluids, and we will see its effect on the vortex crystals. So as you can see, at Mach number 0.5, the initial structure is almost similar. They form a crystal like this. However, for the incompressible fluid, if you keep the movie running, the crystal will not decay. The crystal will not melt, or it will be there forever. I mean, up to your conservation simulation conservation scheme. However, if you have compressibility, we see that after some time, the vortex crystal actually finally melts down like this. So we are trying to find a notion, a meaning of why the vortex crystals are melting. So before we go there, let's do a standard power spectra analysis and see which sort of modes are there. So if you take the power spectrum of the kinetic energy, we see that there are mainly 5 modes present in the system, and we can characterize the modes like this: that it has something which is like if we call it a fundamental frequency, which is omega 0, this one, then you'll see that this is omega 1, or which is the harmonic of this. This will be the beat of these two, and this will be the harmonic of the beat. And this, the fourth peak, will be the beat of this beat and beats harmonic. So these are the main frequencies present in the system. Now, if we go for further, if we increase the Mach number of the system, we see that the width of the peaks are getting broader as we increase the Mach number, which means that there are more scales getting generated. And the power of the peak, that also scales linearly with the number of point vortices. So earlier I just showed one example of 5 vortices. Now if you put several different number of point vortices starting from 2 to 8, and if you divide the power by number of point vortices, it's almost the same. So we can have a relation like amplitude is proportional to number of point vortices time, and we can scale this also like this, and something like number of point vortices time by m squared. This is a quick visual for the two vortex case. How does it evolve? For the 3 vortex case, how does it evolve? And for the something like an 8 vortex case, how does that evolve? Even though for these are for Mach 0.5, and this simulation, these pictures are all up to only 25. If you wait further, you'll see that they finally melt if you have a compressible fluid. So why is these kinds of results observed? So these are some sort of data with Mach number and this startup of this merging process, etc. If you want to ignore that, the final conclusion from this data, you can see if you increase the compressibility, it delays the startup of merging. That means the filaments take more time to reach the point vortices, and it also makes the whole process slower. That is, the engulfment of the individual point vortices to the patch, that is also delayed. And also so this is basically the difference between these. So it prolongs the merging time. However, at m equal to 0, there is no melting. But if you have m with some, if you increase the value of m, the Mach number, you'll see that the melting time, that is when after the formation of the vortex crystal, when are the vortices melting? This melting time is also hastening as the compressibility is increasing. But let's see, why do they at all melt? Basically, what happens is the compressibility generates several group velocities in the system. You can see the movies, you can see the structure here. The peaks are actually broadened here. So they have more different peaks, energy in the modes. So that's why the widening of the peaks I mentioned in the system, and thus continuously perturb. So these different group velocities, these different modes continuously perturb the vortex crystal, thereby hastening their melting process. Okay. So this is why as we increase the compressibility, the melting was happening faster and faster and faster. Now let's go to a different problem, which is identical initial condition. However, the governing equations are a bit different. Let's take a fluid which has a memory effect. What I mean by memory effect is something like a fluid that possesses interaction with its own past dimension, which is the the structure or the energies that previous time can influence not only the immediate previous time, however the more previous time. So it's like an integration on t equal to 0 to present time or something like that. So we simulate this sort of viscoelastic fluid using a standard model called generalized hydrodynamic model. And the governing equations for this kind of fluid is this one. It's almost similar except this term. So if you put tau m equal to 0, you are going back to the standard hydrodynamics. So tau m we call is a memory parameter. So there are several examples of this kind of fluid. One is polymeric or synovial fluid, etc. Before going to the 5 vortex merging problem, let's take a very simple problem quickly, which is the part of the 5 vortex problem, which is, so we isolate the patch vortex, which is the Rankine vortex. So this is the initial after some small time, so the initial condition of the patch vortex. And if you let the vortex evolve, this itself is not a steady solution, unlike the standard incompressible fluid. So it itself grows like this, and for different tau m, that is the memory parameter, they grow differently. And now if we introduce this 5 vortices here, like this, we see that the footprints of these vortices are left here. So it's like the vortices are here, but you see these slight rings around them, which are more prominent if you increase. So this way is I'm increasing the tau m from top to bottom, and this is the time evolution at 3 different times. All are at the same time. So if you increase the value of this memory parameter, you will see these generate these kinds of ring structures like this. And these rings can actually go through one another like this. Here you can see. And they actually interact with each other also. And these are essentially the effects of this memory parameter, which we mentioned earlier. So as you increase the value of this tau m, they generate these kind of structures. So from this viscoelastic part, we see the transverse waves. So these are basically these transverse waves arising out of these point vortices begin to expand and collide with each other, giving rise to regions of higher vorticity. The effect of viscoelasticity is found to diminish the frequencies generated in a compressible system. This part is something I have not shown in the slides. In the limit tau m equal to 0, some frills appear out of the point vortices. And at large tau m, the frills get prominent and form wavefront-like structures and propagate in time. The sort of structures we are seeing here. So as a general conclusion, uniform circular patch vortex, that is a general Rankine vortex, get destabilized and form V states, the structured shapes that I mentioned. Nearby the point vortices help in drawing filaments of vorticity. So if you put the point vortices nearby, they allow the patch vortex to create create and draw the filaments out of it. And these filaments wave break and encircle the point vortices and finally settle down to a vortex crystal for incompressible fluid for the first part of the talk. In the second part, I showed the compressible fluid support several groove velocities. The vortex crystal pattern forms and then melt. And this melting is mostly because of this different groove velocities that are generated because of this compressible fluid. And the melting of the crystal hastens as compressibility is increased. It's clear. And for viscoelastic fluid, I already mentioned that Rankine vortex itself is unstable. Point vortices generate wavefronts, keeping the memory footage, and the wavefronts propagate, collide, and passes through each other. That's it. Thank you.
Okay, thank you, Dr. Mukherjee. So now it's time for question and discussion. Please raise your hand if you have a question. Okay, Mahendra Verma, please go ahead.
Rupak, this good talk. I just want to point out that I think it is a 2D nonlinear interactions which is responsible for inverse cascades that is responsible for the merger of the vortex primarily. Okay, I mean that's my guess. Of course, compressibility can play a role. So we saw very similar things in 2D convection. Though it is different force, but it merges. And also rotating turbulence. So there's a PRL 2013, you can have a look.
Okay.
So good.
Okay.
I think you can explore. In fact, one more comment is that light vortices are connected to analogous to current carrying currents, no, in the same direction.
I see. Okay. Okay.
Comparing the hydrodynamics with the incomplete with the electrodynamics, I mean, basically magnetic currents. There's an analogy, and they attract. So this we point this out in this paper. So I have a look. Maybe something similar is happening.
Okay.
Something similar may be part of your picture. Okay. Thanks.
Okay. Okay. Thank you.
Okay. Any further questions? Okay. Since there is no additional questions, so then I would like to move to the next talk. Thank you again, Dr. Mukherjee.
You're welcome.
Thank you. So next